Okay, now it's going live on YouTube. Let everybody else in from the waiting room. And so we'll have 2-minute warning for the longer talks that are today. The speakers just asked to advance the slides. You can annotate if you want, as we discussed. And for questions, please use the chat. We will ask for all these talks, and in the interest of time, speakers can answer the questions in the chat. And then when we get to the discussion, people can please use your raise hand feature, which is under the reactions button. Then we can make sure to call on everybody and unmute you so you can join the discussion. And with that, so today's sessions are going to be 2 different sessions, also in shallow clouds. The first one is focused on ships and volcanoes. These are all under the theme of sort of natural laboratories or opportunistic experiments to look at aerosol forcing. And then we're going to talk actually about some COVID and experiments, and then looking at trends. So we're going to start off with Matt, who's been leading an effort. Matt Christensen has been leading a ACPC effort to come up with an overall review paper of all of these experiments. And it's some very interesting stuff. So take it away, Matt. I'll give you a kind of a 2-minute warning when it's time.
Thanks, Andrew. So yeah, this has been an effort co-led with Andrew Gettleman and 30 some other co-authors broadly within ACPC, looking at synthesizing the breadth of the literature on natural laboratories and opportunistic experiments. So I'm not going to go through all of this work because there's a lot to dig into here, but just sort of to provide a broad overview of the topic and some definitions of what we mean when we describe a natural laboratory versus an opportunistic experiment. And so, this is a satellite image of ship tracks. This is one of the most prominent manifestations of an aerosol indirect effect that we know. And they're quite striking features. And we'll go into other natural laboratories which may not be so evident when looking upon them from space. So yeah, thanks. I'll say next slide next. Okay, so these are, so basically an opportunistic experiment we're defining as an injection of aerosols into an environmental regime, which would be sort of a laboratory of such, where the unperturbed state is to some extent known. So opportunistic is used interchangeably between sort of natural, which would be volcanoes, and human cause, which would be things like industrial plumes and ship tracks. So broadly, a laboratory refers to an environmental, to a regime or type of emission, while an experiment refers to a particular case. So when we start to look at the experiments that we're considering, we have things like, the laboratory might be ship emissions, but within that laboratory would have things like ship tracks, ship corridors. The same thing goes for volcano emissions. We have volcano tracks and volcanic eruptions, which have an imprint on a very large region by comparison, and so on. And then there's also particular events, such as weekly cycles of aerosols caused by human activities, which can be observed in changing cloud properties. Even hemispheric differences between northern and southern hemisphere, you can observe that as almost a natural laboratory of such to understand aerosol indirect forcing. And so this sort of borne out from many of the excellent presentations on this topic last year, and this is now sort of being turned into a review paper on this topic as a whole. And so this figure here is kindly provided by Anna Posner in one of her previous articles, and sort of including a range of these different laboratories in a single context for aerosol indirect forcing. Next slide. Next slide. So here are just some examples from of these natural laboratories or experiments from satellite. So the industrial emissions at the very small local scales, we can see very fine tracks from industry. These occurring in Newfoundland in the upper left-hand panel. But then as you get to sort of larger and larger scales, you can have entire megacities affecting clouds. And this is sort of the work that Bellatoll has recently done. And ship emissions laboratory, we have individual ship tracks, which have been studied extensively. and shipping, shipping corridors also have an impact sort of on the broad scale clouds. And here you can, it's not so easy to detect an individual shipping corridor per se of an imprint on the cloud system. You have to do something clever like create a counterfactual through some method to remove the background, so you can actually observe a perturbation in a statistical sense. So some of these experiments occur at different scales, require different methods in order to extract a counterfactual. It's very easy to do this at the local scales where you have individual tracks. It's much harder when the emissions are spread over broad regions. And similarly, we have fire tracks in the lower left-hand corner, and then the famous last year's event with the West Coast fires creating a massive plume covering an extensive region of the Pacific Ocean and then being advected across the US and even into the Atlantic. Next slide. Okay, so there are several databases now available to look at these individual track studies. So going back to days of Coakley in his group at OSU developed a ship track database of over 4,000 hand log ship tracks. I was in his group and I developed another database, but was more co-aligned to the Calypso CloudSat track to understand the vertical properties of ship tracks. We also have several industry tracks that Velatol, Handlog, and then Ed Greisbeard also did a lot of hand log ship tracks to look at the effects of policy changes near these in the SECA zone, they call it, where you have a reduction in sulfur emissions from ships that were mandated, and looking at changes in the percentage of ship tracks occurring in these zones and their brightness and features. And then Tiano Llanes recently developed machine learning capabilities to identify them automatically. And we also now have a nice network of passively degassing volcano estimates from Cairn. Next slide. And then Aerocom also leads a Volc ACI initiative, which sort of pulls together a broad network of these effects across a whole wide range of atmosphere models, which is very useful to understanding these processes for volcanic eruptions. And then we also have a number of field campaigns over the years, MAST probably being one of the earliest to really dig into understanding the extent to whether or not the emissions from ships produce tracks or not. And then the MAIS, EPEACE, and ECRUISE studies kind of drilling into other aspects of ship tracks. Next slide. Okay, so in this talk, I'm just going to briefly summarize sort of the results of 60 papers that we've synthesized in this group in sort of a meta-analysis study looking at broad changes in cloud properties, effective radius, liquid water path, to see if we can sort of understand variability in these properties. And so we're doing this in terms of categorizing each experiment as to whether it's a ship track, fire track, industry track, et cetera, and whether the data came from satellite in situ, large eddy simulation, and so on. And this is sort of showing a snapshot of what the table looks like. Next slide. So broadly speaking, this analysis has about 60 different estimates, and the numbers are shown on the left-hand panel. The in situ ship tracks had the largest number of papers that were synthesized, but then some other studies have fewer observations of different laboratory or different experiments. And what we see in general is that all the studies agree that droplet sizes decrease in these experiments of opportunities, but liquid water path variations are in both directions, negative and positive. And they all tend to agree that cloud droplet sizes increase. Next slide.
2 minutes, man.
Okay, thanks, Andrew. And another point to make is that when we normalize by the change in the droplet number concentration as a function, or as effective radius as a function of ND, or liquid water path, we can start to see that some of these effects of dilution tend to become less of a problem, because you now are taking the change in ND, taking the liquid water path, the effective radius, and divided by the change in ND, which allows for better normalization across all of these different experiments. And what we can see is that starts to become slightly better agreement when doing this, although the liquid water path response is still widely variable. And if we go to the next slide, the final slide, actually, it sort of hints to the fact that there's a lot of different controlling factors that are influencing these laboratories that is a reason for this diversity. So one of the big ones is the meteorological effects. As you know, we know as the air above the boundary layer gets drier, the clouds can tend to desiccate more easily if they become polluted in these pollution tracks. Another key component too is that there's actually a lifetime effect built into these systems. As the clouds age, as they move down away from the stack, the properties change over time, and this has a big impact. And whether or not, if they live long enough or not, could have it impede our ability to use them as proxies for understanding climate change even. So with that, I will leave it. For any questions, we'll move to the next speaker. Thank you.
Thanks, Matt. That's a great overview. I think we'll move on right to the next speaker so we can stay on time, and we'll have more time for more detailed discussions when we get to the end of this and the discussion at the end. So
sounds good.
Next up is Franziska.
Thank you. Yes, thanks. Yeah, I feel it's really great to kind of finally present to this whole ACPC audience our arguments related to timescales on why we may actually be overestimating aerosol cloud climate cooling if we too directly rely on ship track data. And next slide, please. And in more detail, what I want to talk about is how to properly quantify liquid water path adjustments to aerosol perturbations in non-precipitating stratocumulus. And this cartoon illustrates the main chain of processes that we are dealing with, where the important point is that smaller droplets mean an enhancement in entrainment and evaporation, which reduce liquid water path, which I've illustrated here by the cloud getting somewhat thinner. And now the point is that when we look at our data sources, then it's actually not so clear how strong this effect is, this liquid water path adjustment caused by aerosol effects on entrainment and evaporation. So when we consider ship tracks shown here in pink, then they report almost no effect, which corresponds to these flat slopes. In contrast to that, satellite climatology typically gives much larger adjustments corresponding to much steeper slopes. And you may see that actually the slopes from the satellite climatology can be so steep, corresponding to such a strong adjustment effect, that we touch upon this orange region, which I've labeled cloud darkening. So this would actually be the region where the reduction in liquid water path is so strong that it overcompensates the TUMI brightening, such that the net effect of adding aerosol to a stratocumulus cloud would actually be a darker cloud. And we've also seen this effect in some presentations yesterday already. And so our argument is that we can actually understand this discrepancy between the ship tracks with their nice causality and the more climatological satellite studies if we take into account the timescales that are associated with these different processes illustrated in the cartoon. Next slide, please. Okay, so this, I'm sorry, this is only a part of the slide. So the point I wanted to make, and I can make this like just tell it to you, is that when we think about the TUMI effect, the timescale of the TUMI effect is something like 10 minutes. So basically, this is the time it would take a newly activated cloud droplet, which has been activated in a polluted environment, to travel all through the cloud to cloud top. So you can say this happens in 10 minutes. It's a very short time. In contrast to that, our main result is that if you want to observe the liquid water path adjustment due to aerosol effects on entrainment and evaporation, you actually need to account for a time scale of 20 hours. So much longer. And I cannot go into the details here. For this, I have to refer you to the pre-recorded presentation that I think has been shared in the chat. I only want to mention that we use an ensemble of large eddy simulations and Gaussian process regression to obtain basically this flow field, which is a sophisticated version of a droplet number dependent liquid water path budget. And now I would like to move on to the next slide, which hopefully looks like it's supposed to look. Well, it's somewhat better, but still not fully complete. I really wonder what happened here. But let's just continue. So I just told you, and you have to believe me, that there are certain timescales in the response timescales that control the response of clouds to aerosol perturbations. And these timescales are specifically 20 hours for the liquid water path adjustment. Now we need to compare that timescale to the timescale of the pollution. What do I mean by timescale of pollution? For example, a ship track is a rather short-lived pollution. So we can say that typically when you observe a ship track, it has been the cloud has been exposed to the exhaust from the ship for maybe 3 hours. And these 3 hours are longer than the 10-minute timescale that I tried to explain for the Toomey effect, which is the reason that we actually observe the brightening of the cloud. But these 3 hours are much shorter than this ominous 20-hour timescale, which I've mentioned, which it takes for the liquid water path adjustment. And so this basically means that the cloud in the ship track returns to its pristine state before it has fully time to respond to the liquid water path adjustment. And honestly, I really think maybe I can briefly share my own slides.
Francisca, I have the slides. If you stop sharing, Jihu, I can actually share them quickly.
Yeah, because I feel like here it becomes a little
so
complicated.
Please stop sharing them because I'm actually looking at the here. How's that?
Yes, so here, this is what I wanted to show you. We have a 10-minute-hour timescale for the Toomey effect, and we have a 20-hour timescale to actually observe the cloud getting thinner due to a reduction in liquid water path. This was basically also on the previous slide. So ship tracks are short-lived, and that means there is not enough time for the liquid water path adjustment to really evolve before the cloud gets back to its pristine state, which then explains why there is a weak liquid water path adjustment. And this is in stark contrast to the situation we are actually interested in when we think about the aerosol forcing and the pre-industrial versus the industrial background. Background already indicates that we have a much more persistent pollution. And we can actually say that these backgrounds persist for something like 48 hours, 2 days. And this timescale comes from the timescale of boundary layer evolution and also corresponds to the lifetime of a typical stratocumulus cloud deck in the subtropics. The point is that this background timescale is long enough compared to the 20-hour adjustment timescale to allow for the adjustment to take full effect. And the plot kind of formalizes this argument a little bit. So what you see here is, so the adjustment is time dependent, and we can derive an expression how the adjustment decays to its final value with this timescale of 20 hours. And now we can plug in different pollution timescales. So if we take the time dependence and put in a 3-hour time, which would correspond to a ship track, then we get a rather weak adjustment, as shown here by the pink slope, which roughly corresponds to the reported values for ship tracks. If, in contrast, we put in the 48 hours from the climatology, there is much more time for the adjustment to evolve, and we get a much steeper slope corresponding to much stronger adjustments. Now you may say that actually this adjustment is somewhat too strong compared to the satellite studies. The reason for this probably is that we have assumed very dry above cloud conditions in our simulations. So we have kind of set up a situation where we have the maximum effect of aerosol and entrainment and evaporation, which means that the values we derive is a lower bound for the adjustment. In other words,
2 minutes.
In other words, thank you. In other words, the typical above cloud moisture in the climatology is probably not quite as dry as our simulations that we have used. And Andrew, could you please go on to the next slide, which already is my conclusion. And instead of a usual conclusion, what I want to discuss are 3 points where I think that the time dependence of liquid water path adjustment really matters. And the first would be opportunistic experiments, or more specifically comparing opportunistic experiments. For example, if we want to compare results from a ship track to a shipping lane, it may be worthwhile to keep in mind that the shipping lane will somehow effectively have a longer exposure time of clouds to pollution. So we would expect stronger liquid water path adjustments. Similarly, if we now want to use, let's say, ship track data to learn something about the aerosol forcing, it may be worthwhile to consider whether we can use equations that describe the time dependence of adjustments to actually extrapolate these short-lived pollution situations to maybe climatologically more relevant timescales. And then last but not least, if we think about marine cloud brightening, then we certainly want to avoid these negative liquid water path adjustments as much as possible, which means that one should try to keep the exposure time of clouds short to the pollution. Thank you.
Thank you. Sorry about that. Let's keep moving. Francisca, there's actually a comment in the chat. Let's see, hopefully the next presentation will work fine. So let's see, is Bella unmuted? Check.
Yeah.
Yep, okay.
Hello.
Go ahead. Yep, I can hear you.
Thank you. I will talk about ship track like industrial polluted cloud tracks. So here you can see with the cross is marked industrial aerosol source, and in gray here is industrial polluted cloud track. Next slide, please. So previously I have used MODIS snapshots to study such polluted cloud tracks. But here we use geostationary SEVIRI data. Here again on the top you can see one track, SEVIRI cloud droplet effective radius, and based on the effective radius for each time step, we classify SEVIRI pixels as polluted and unpolluted. So at the bottom figure, polluted pixels in red, unpolluted pixels in dark green. And using geostationary data, we get time series for the polluted cloud properties and for unpolluted cloud properties for each track. So we have something like 150 tracks sampled in such a way. Okay, next slide, please. This is here one example for Moscow. So here in these images, location of Moscow is given with the cross, and to the south east of Moscow, here is polluted cloud area. So in this area, there is strongly enhanced cloud droplet numbers, but here in these images, you can see liquid water bath in color. The time difference between the top and bottom figure is 2 hours. So if we start from the top, so now in time, the cloud water increases in the polluted cloud area. And after 2 hours, the cloud water is strongly enhanced compared to the nearby unpolluted cloud area. So most likely due to suppressed precipitation in the polluted cloud area. And it would be extra nice to get hands on some ground-based precipitation radar or cloud radar data to get more process understanding of that. In principle, it should be possible. Next slide, please. Okay, so this is the overall result. So now taking all the cases together, 150 cases or so, and here 2 images, both are time series such that on x-axis we have time with sunrise, time coordinate 0 and sunset 1. And on y-axis we have a Toomey effect plus adjustment divided by the Toomey effect. So since the sunrise early morning, we have a decrease in cloud water offsetting large part of the Toomey effect until the noon time. And then since the noon, there's increase in cloud water, and in the afternoon, there's already quite strong increase in cloud water on average, so that we get enhancement of the Toomey effect. So now this is here all cases taken together, but on the right-hand side, now we create 2 groups of cases. So one group in orange with strong increases in cloud water with likely suppressed precipitation, another group in green with aerosol enhanced entrainment, with weak change or decreasing cloud water. Well, we see the same thing that in this precipitation suppression cases, in the afternoon, we see this gradual increase in cloud water. But in case of this green group, in some cases, we do see very strong decrease in cloud water. But as a matter of fact, the cloud water is already decreased since the sunrise, and there is no further decrease during the day. So this perhaps suggests that aerosols act to decrease cloud water more likely during the nighttime, and we get this day-night contrast here, at least in the European part of Russia, in this cloud regime. Okay, next slide, please.
2 minutes.
And finally, some points for discussion. So how to better observe the temporal evolution of cloud responses. So one option, of course, would be large-scale statistics based on geostationary data, what has not been done in detail yet. Then Ed will later show some analysis of along ship tracks. So I think combining Ed's work with this geostationary analysis, so Ed has used the MODIS data, but using geostationary data to also look the evolution along the track could perhaps help. And regarding the Franziska's work, I would say that she makes an excellent work quantifying the time scale, but really one problem I think is that she uses nocturnal radiation. So what is the role of the diurnal cycle? And perhaps it is very important to have realistic diurnal cycle, because diurnal cycle is probably quite important in many cloud regimes. Okay, thank you.
Thanks, Ville. Quick question. So I would assume if the diurnal cycle is important, it's more important for these industrial tracks over land than it would be for cases over the ocean. Is that, you think, for things like ship tracks?
Perhaps, but we know that diurnal cycle is very important in subtropical stratocumulus, for example, as well. So one thing is that how important is diurnal cycle for the unpolluted clouds, for clouds in general. But now if we have perturbation, how important is diurnal cycle for that? I think this is perhaps not as straightforward that in case in unpolluted clouds, it's not that important. We cannot be sure that it's not that important in case of perturbations, because all these processes play around.
Okay, thank you. Let's go on to our next talk. Michael Diamond is next.
Great, thanks, Andrew. And you might notice I've changed my title a little bit from the advertisement. Hopefully this fits a little bit better. And I wanted to kind of go at this question of how worried should we be about semi-direct effects when using natural laboratories to study ACI when we're normally thinking about indirect effects. I'm going to have two quick stories, one about fires where I think the answer is pretty clear that we need to care about this, and one about ships where I'm still trying to make up my own mind on this. Next slide, please. Great, so for the first case we're going to go through real quickly here, this is a modeling effort of the stratocumulus to cumulus transition in the Southeast Atlantic, where if you follow the kind of peach dots there, that's basically the route the clouds are taking on their transition from overcast stratocumulus decks to more broken stratocumulus under cumulusines that we observed during some field campaigns in 2017. What's going to be important for this talk is just to know that there are two different model efforts going on here. One, I'm using a regional climate model, WRF-Cam5, to simulate, if you see on in a simulation, that means the case has all smoke effects. If you see off, there are some subtle differences, but just think that that's smoke turned off. And that can capture large scale smoke circulation interactions. I then take those free troposphere, thermodynamic, and aerosol outputs and force an LES model with them. And that way we can both resolve the cloud layer better, but also now I can kind of mix and match different free tropospheric aerosol and thermodynamic properties to try to isolate effects. So if we move on to the next slide, please. One big thing we found, and I'm only going to give kind of highlights here, is that there's a reduction in large-scale subsidence over the basin due to large-scale smoke circulation interactions, or really this is just saying that smoke absorbs a lot of sunlight, and instead of just going into heating of the layer, a lot of that energy actually goes into the work of reducing subsidence by, at peak, kind of about 100 meters per day, which has quite strong effects. So if we move on to the next slide, please. I'm now going to put that subsidence reducing effect into a large eddy simulation model. So what I'm running here in black, the black line here is the large eddy simulation model forced with all of the WRF smoke related fields. So how smoke has affected temperature, moisture, subsidence, etc. In red here, I'm doing that exact same run, except I'm only swapping out the aerosol number. So this is a relatively quote unquote clean case. And in purple, I'm doing the same thing, but only swapping out the subsidence. And you can probably see a lot of cool effects here, but I'll bring your attention just to the cloud fraction and cloud rate of effects. Those matter most here. It turns out, at least in this specific case that we're simulating, the semi-direct effect of reduced subsidence is more influential on the cloud evolution and the ultimate forcing from these clouds than the order of magnitude change in aerosol number, which I found personally very surprising. That's probably because even in the base state here, we were not generating much precipitation. So when we are thinking about these fire laboratories, especially because we do have these very absorbing aerosols, these semi-direct effects are quite important, and a problematic thing for us to study at small scale models and small scale observations is that this absorption can have large effects. So very similar to what we were talking about yesterday in terms of aerosol meteorology, not just being covariability, but also partially causation. Next slide, please. Great, I want to end by talking a little bit about whether or not this is relevant for ship track and shipping lane work. So Matt already showed the kind of first image here where we were looking at a shipping corridor in the Southeast Atlantic. And one thing I want to highlight from that work is that we found a reduction of liquid water path in the afternoon, which we originally interpreted as an entrainment effect, very similar to what Franziska was showing earlier. Next slide, please. However, in that paper, we didn't just assume it was an entrainment effect, we also did try to rule out the possibility that it could be a semi-direct effect. So what I'm showing here is the factual, by which I mean the just standard MERA2 output of surface black carbon. So that's what our best idea of what we think actually happened. The counterfactual there using a statistical technique called Kriging that I won't really go into the details of now, but you can take the difference between that factual and counterfactual scene, and the difference there can be interpreted as the effect of shipping on black carbon over that area. And if you do some pretty simple Beer's law calculations with what I consider to be fairly generous assumptions for BC absorption, you get a heating rate in the subcloud layer of about 0.001 Kelvin per hour. So something that would be pretty negligible and something that I felt comfortable ruling out as an hypothesis. Although one caveat here, I should say that I was using the climatological perturbation of BC. So maybe there's more of an enhancement in individual track. If we move on to the last slide here, the reason I'm bringing this up now, so I'd say, if you asked me last year, my answer would be, at least outside of fire tracks, probably no, we didn't need to worry about semi-direct effects. But there's recent work that I think Danny's going to talk about next that's maybe making me reevaluate this, or think that this is maybe a bigger question we need to answer. So in work from Danny and Yenny and colleagues, Hu et al. Out this year, they stratify the same case in the Southeast Atlantic by background aerosol or cloud droplet number concentration. And what they find at very high what they interpret to be background number concentrations is an actual reduction in ND, which they hypothesize could be due to a semi-direct burn-off effect. This would obviously require a very substantial amount of heating. It would be a very strong effect. I don't know if I totally believe this. I think this could potentially also be interpreted as some kind of reversion to the mean statistical effect of their sampling or something else, but I think it's worth addressing. So I kind of want to just leave that out open to the community. And that's what I have. So any questions, I'd be happy to address either here or in the chat.
Thanks, Michael. So you think this might be, even despite your calculations, you think this might be significant, or this is a different mechanism for the black carbon than you were considering before, which is a deactivation mechanism?
I'd say I was extremely certain last year that the below cloud semi-direct effect wasn't driving liquid water path results I found. I think after reading this paper, I would adjust it to be, I think it's more likely than not that I was originally correct and that the semi-direct effect isn't playing a role, but it's giving me enough pause that I think it deserves some serious effort to try to quantify.
Okay, thank you. Next up is Danny.
Yeah, okay. Thanks for the introduction of my paper. Okay, this is a paper which is by Shuang Hu, who is co-advised by Yanyan Zhu in Nanjing University, and by Feiyu Mao in Wuhan University, of course, co-advised by me. Next slide, please. So here we focus again on the shipping lanes. And what happened here? Why can't I get rid of the annotation? Anyway, and with the focus on the background concentration, Michael Diamond has shown that climatologically it gives minus watt per square meter when applied to GCM. But here, the main point of the paper is that the forcing depends strongly on the background concentration of the droplets, and that has implications of how we should apply it to calculating the global forcing. Next slide, please. Clear all drawing, okay. So here I show the figure that Michael showed already, where we see the perturbation of the drop concentration compared to the background as a function of the background drop concentration. And you can see that the effect, the anomaly, positive anomaly increases with a smaller background concentration down to 20 drops per centimeter cube. But at high concentrations, we have actually decreasing of drop concentration, possibly because of the cloud burning effect. Please note that when we have these stars, it is significant statistically. This faint line is the number of cases. So while Michael calculated the average forcing, here we took the situations where the background was very high, and with already high background concentration of black carbon from land, with the addition, the supersaturation already is very high, and it doesn't take much decreasing of the supersaturation by the additional black carbon to decrease the substantially the drop concentration, and therefore have the positive effect. That is my interpretation how we can resolve the question of Michael. Here we have the same for the cloud fraction anomaly. And we see again that it increases with a cleaner background and has a apparent cloud burning effect in high background concentration, which is relatively rare, as you can see here with this line. And the effect on the liquid water pass was not consistent and not significant, so I even don't show it. You can see it is presented in the paper. But when we did it both for the morning overpass time of MODIS and for the afternoon overpass time of MODIS, and in the afternoon we got much or significantly larger effect of cloud burning, as manifested here, and therefore that supports the hypothesis of cloud burning. Next slide, please. Of course, the cloud radiative forcing anomaly with respect to the background is what we are interested in, and we see again it increases quite strongly with cleaner background, and a positive anomaly in the polluted background. And here you can see the numbers. That clean background is less than 60 per centimeter cube, and polluted is larger than about 100 per centimeter cube. So let's go to the next slide, please. So if we look at the background cloud drop concentration, this is actually the background cloud drop concentration, and we see the cloud radiative effect, which is the blue line, how it changes. It is decreasing with the cloud drop, background cloud drop concentration, and it is divided about equal between cloud albedo and cloud fraction. However, if we go to the relative contributions of these two components, this is a zero line, we see that the cloud fraction effect in the red line is decreasing towards zero when the background goes to 60 or so, and the albedo component, of course, increasing. But that increase doesn't mean much because the absolute amount of the brightening vanishes by about 60 drops per cc. So that fractional change doesn't mean much.
2 minutes, Danny.
Okay, next. Next slide, please. So this is the last slide. So the implications are, I think, quite substantial, since nearly 50% of the global oceans have background drop concentrations smaller than 50 per centimeter cube. A small amount of anthropogenic aerosols can have much larger cloud-mediated radiative cooling than globally average -1 watt per square meter, as calculated by Michael Diamond in his latest paper. However, this strong cooling effect can partially be compensated by the cloud burning, which has a positive radiative effect when the background is rather high, but it happens over much smaller area than the pristine area. So all that needs to be taken into account when we do when we propagate it towards a calculation of global forcing. Thank you.
Thanks, Danny. Question from Andrew Williams. So is this the background calculation? Are you doing it with the same kriging effect that Michael used, or is this just a separation of regions?
It's the separation of the region is, well, I already took the shipping lane as we know it from a previous study. And we just, if you go to the second slide, you can see that it has two adjacent, please go back to the second slide. No more. Yes,
Yeah.
you see area B is the shipping lane, areas A and C are the background, and we are looking at the concentration of the shipping at area B compared to area C and A in latitudinal bands of a few degrees.
Okay, so it's sort of a similar method to the kriging. Okay, we'll move on. Danny, there's a couple more questions in the chat, so if you want to take a look at those.
Okay.
And so next up is Ed. You unmuted, Ed? We need to do that.
Does that work?
There you go. Yep, that
Excellent.
works.
Yeah, cool. Thank you. Yeah, so I suppose you can go on to the next slide. I'm going to be talking about the timescales of aerosol cloud interactions with ship tracks, because that's what we're talking about at the moment. Next slide, please. So I mean, most of you have seen this kind of idea before, but I suppose why do we care about the timescales? I suppose one reason is that satellites kind of quite easily measure climatology, but models in general are calculating process rates. So maybe we want to kind of get a better, closer link to what we're actually calculating with the models. High resolution cloud models are expensive to run. So you want to know if you're running it for the correct time period. And as Francisca showed us earlier on, we want to make sure we're measuring the correct thing. That if we're using ship tracks to constrain aerosol cloud interactions, are we actually measuring the correct time scale for that? Next slide, please. So the basic kind of idea behind this is that you can use a ship track as a kind of record of how a cloud has changed over time. So if you know where the ship was and you know what the wind field looks like, you can work out how long ago the ship emitted aerosol into the cloud at each point along that ship track. And so that's what we have here. The thin black line in there is kind of the estimated track of the ship track. So it follows the ship track where we have the ship track, and it's interpolated with winds where we don't. And you can see on the bottom here, the red line is the droplet number concentration inside the ship track, and the blue, the droplet number concentration outside the ship track, as a function of the time since emission. The important thing to remember here is that you can, although you can chop the ship track up into chunks, it's not the record of the evolution of a single cloud. Each point on the ship track is essentially a separate cloud, and you only get one view of that cloud with this MODIS snapshot. So here what we want to do is then composite a whole load of ship tracks to try and build up, I suppose, a composite picture of how a cloud in general behaves after it's had aerosol emitted in or injected into it. So next slide, please. So the first thing we might care about is how does the droplet number concentration change? And in general, we see that the droplet number concentration, in this case, this is the enhancement. So how much bigger is the droplet number concentration inside the ship track compared to outside? We see there's a fast initial increase in the droplet number concentration within an hour or so. And ships with higher SOx emissions tend to produce a larger droplet number concentration enhancement, which is nice. And this signal then decreases with time as it kind of mixes away and your aerosol source is depleted. Now this relationship here is strongly impacted by the local meteorology, the cloud background state, loads more things it's worth having a look at in the paper if that's something you're interested in, because there's not really time to cover that now. Next slide, please. The liquid water path enhancement shows a couple of other features. So we see an initial kind of decrease in the liquid water path, followed by a gradual increase for the ship tracks that we looked at over the kind of 20-hour period we were looking at. Interestingly, the change in liquid water path doesn't seem to be very sensitive to the size of the aerosol perturbation. So there's clearly something else going on that determines how sensitive that cloud liquid water path is to the aerosol that's injected into it. Next slide, please. And of course, because these two things are varying together over time, if you don't take that time into account and just look at all of your ship tracks together, you actually find that as the droplet number concentration decreases over time and the liquid water path increases over time, you find this negative relationship between them. So if you don't account for time here and just treat all of your ship tracks together, you don't retrieve the correct, as it were, liquid water path sensitivity to droplet number. And in this case here, all of these ship tracks have the same, or on average have the same aerosol perturbation, or all of these points have the same average aerosol perturbation. So it's really not the droplet number impact on liquid water path that we're looking at right here. Next slide, please. So instead, what we can do is we can look at each time segment along the ship track and say, how does the droplet number change from outside to inside the ship track? And how does the liquid water path change from outside to inside the ship track? So there's a lot going on here. You concentrate on the middle plot, or just the plot in the middle. This is showing that sensitivity. So how does liquid water path change as a function of the change in droplet number from outside to inside the ship track? And in general, we find it's negative. So there's a decrease in liquid water path as the droplet number concentration increases going into the ship track. But that change in liquid water path depends on the background cloud state. So in cases where the droplet number concentration was relatively low, you find an increase in liquid water path kind of appearing over time. It doesn't appear instantly, but over time that liquid water path gradually increases. And for clouds that were relatively polluted beforehand, the liquid water path decreases further over time as the droplet as time goes on.
2 minutes.
Excellent. The thing that really concerns me about this plot is that the liquid water path sensitivity appears almost instantly. So although the droplet number concentration changes, and you would expect it to change very quickly, you wouldn't necessarily expect the liquid water path to change instantly, and yet it appears to. And this may be indicative of perhaps a retrieval error, maybe in the effective radius. And so, but it's not necessarily clear exactly what that is yet. But yeah, I do find that a bit concerning. Next slide. The other thing here, as you might expect, this sensitivity also depends on cloud top humidity. So in cases where the humidity is higher, you tend to see an increase in liquid water path with increasing droplet number over time. But it takes a bit of time for that increase to start to appear. In this case, we only really started seeing a change after about 4 hours. Okay, so if you click forward 2 slides, that'll go to the conclusions. And again, excellent, yeah. Oh no, it's okay, we don't have time for that one. Oh. Okay, if you just go to the conclusion slide, summary, something, the last slide. Excellent, yeah. Yeah, so, I mean, as I was saying, clouds are not constant with time, but we can use these isolated aerosol perturbations to look at how things change over time and the timescales of this cloud response to aerosol. There's only really kind of very broad overview of the things we looked at here. There's quite a lot more in the paper. So if you have any other ideas or questions, let me know.
Thanks, Ed.
Thanks, Ed.
Question from Viola Toll. Can you see the temporal evolution along an individual track? Or does the response come from a small number of long tracks that you can track for 20 hours?
Yeah, so not in this case. So we have to use the composite because you only get a snapshot. So when you're looking at an individual track, you've got lots of points, you know, one point that was 30 minutes behind the ship, one point that was an hour behind the ship. And because those clouds have different backgrounds, it doesn't give you the development of the individual cloud. So you need geostationary to do that. And that's on the list of things to do.
Okay, great. Thanks very much, Ed. Next up is, let's unmute Manoush. There we go. Okay.
Okay, hello everyone. So here in this talk, I want to address the impact of the additional tropospheric aerosol due to volcanic eruptions and the liquid body clouds. Next slide, please. So as a first case of a study, we simulate Holoran volcano by ICANN-WP from 1 to 7 September 2014 in a regional domain, as you can see here, with approximately 2.5 kilometer horizontal resolution. And we also use double moment cloud liquid and ice microphysics scheme. And for the initial and the boundary condition, we used IFS data, and then we compare the results of the simulation to the satellite observations. So next slide, please. So ICANN-WP is not an interactive aerosol model. So we developed a new approach to read and interpolate the number of the CCN during the simulation. And in order to produce this input for the model, we use the CAMSRI analysis. And we perform Abdur-Razak and Gunn parameterization to the aerosol composition, and we drive to the number of the activated CCN as a maximum of the supersaturation, which this part was done by running a box model. So next slide, please. And we also implement a MODIS simulator in the COST package into our simulation in order to have the opportunity to have a better comparison between the simulations and the observations. So next slide. And I also needed to know how the SO2 plume looks like during the eruption and how it evolves during the time of the simulation. So in order to get this data, I use these OMPS satellite retrievals, which produce the total vertical column amount of SO2 in the lower troposphere. So these data first help me to include the aerosol, the volcano emissions to the simulation. And also the idea was to look at the macrophysical variable inside and outside of the plume. So by using this data, I proceed the analysis. Yeah, so next slide, please. So here we want to look at some PDF plots, for example, for effective radius here. This is for outside the plume for control run, which has the background CCN concentration. And this is for perturban. The blue curve is for perturban. And the black curves is for MODIS. As you can see, the outside and outside the plume between control run and the perturban, we can't see so much differences. But the MODIS in general has the higher probability over smaller values of the effective radius compared to both simulations. So next, please. This is the same image for inside the plume. As you can see, in the control run between inside and outside the plume, we can't see so much differences. But in the perturb and MODIS, we can see a shift toward lower values of effective radius compared to outside the plume. So next, please. And we also assess the cloud droplet number concentration. If we compare the red lines, we can see that in the control run, there's not much a difference between inside and outside the plume, but for the perturb and the MODIS, we can see that there's a higher probability over larger values of ND inside the plume compared to outside the plume. So next, please. And we also looked at liquid body pass. So as you can see, and outside the plume, there is not much difference between the this perturb and the control simulation. But inside the plume, we can see that the liquid body pass increases in the perturb simulation compared to control run. And if we compare these two black lines, we can in the left and the right panel, we can see that inside the plume, liquid body pass is larger in the MODIS data as well compared to outside the plume. So next, please. So here, as a conclusion, I can say that in this part of our research, we found a positive correlation between enhancing the ND and the liquid body pass. So thank you.
Thank you, Manoush. So I have a question. So you had a plume. What is the difference between the control run and the perturbed run? Because there was a plume in both.
No, in the control run, we ran the model with the background CCN concentration. And in the perturbed run, we impose the plume to the simulation.
Okay. So
Yeah.
but you had an inside and outside the plume in the control run, but that doesn't make anything. Shouldn't
Yeah,
actually matter, right?
yeah,
That's sort
we
of
looked
just a
at the
test
same
of the-
region. Yeah, to see
So
how the
that's to try to sort out the meteorology because you get the same meteorology.
yes.
Okay, so that helps determine if there's a meteorological effect because there is no plume. You're just taking those locations with the meteorology. Okay,
Yes, yes, true.
great. All right, well, thank you very much. We'll go on to our last talk of the session. Yan, let's see if
Can you
are
see
you
me?
unmuted now? Yep, there we go. Go for it.
Let's start.
Yes.
Okay. So today I'm going to present my our recent work based on the volcanic aerosol. This work is between the collaboration between me, Danny, and Professor Fei Mao from Wuhan, and Xin Wang, PhD candidate from Wuhan University. Next, please. So here is the background. Because summer of 2018 is a remarkable period of volcanic eruption of the South Pacific. And we know we want to check the reaction of marine shallow clouds to volcanic emission is serving as a natural laboratory, as we talked a lot for quantifying the aerosol cloud interaction. So we can see the remarkable eruption, which release sulfur dioxide mass remarkably during the summer. So next, please. So what we want to check is we want to check the variability in ND, which is dominated by the variability in volcanic aerosol rather than meteorological. Here we used the MODIS level 1 and level 2 data to retrieve the ND and ND core as we did before, and also the aerosols from MERA2 SST and also the atmosphere profiles from the NCEP data. So the table is the parameters which we derived from the data. Next, please. It seems I have some delay. Okay, so now I can see it. So on the left panel, you can see the box plot when the background sulfur compound. So sulfur compound is defined as SO2 plus SO4 together. So we can see when the sulfur compound is greater than the mass concentration is greater than 10 power of minus 8.6 kilo per kilo, the ND exists 40 per cc. So we use this threshold to find the volcanic eruption dominated area. So on the right panel, it is a distribution, and we divide this region to two volcano clusters. So as you can see, one is close to the Vanuatu, which we call the southwestern volcanoes, and another one is Galapagos, we call the east volcanoes. Next, please. So because the cloud geometric thickness could represent most of the meteorological changes, therefore we binned the data to different cloud geometric thickness bins, as we show in different color of lines. So if you look at the red circle, we can see the cloud fraction is increasing with the increasing ND. Also on panel D and panel H, it shows the cloud radiative effect, which is also getting stronger when the ND increases. But we can see for both volcanoes, they are showing different slopes, which means the cloud properties to ND perturbation has different response. So we checked the meteorological and the environmental conditions for these two volcano clusters. So on the panel B, on the right panel, we can see for the eastern volcanoes, it has larger LTS, relative humidity, and lower SST, which are all feasible for more cloud cover for the same ND. So this is the meteorological conditions actually explains why the east volcanoes has a larger cloud fraction. So let's go to the next. So next we want to really check if the external enforced volcano aerosols lead to different impacts of change of the cloud properties compared to the aerosol and the cloud properties which may covariate with the meteorological. So what we do here is we calculate the global ND and the cloud properties on 2014, and we on the panel A we actually filtered the the data with a similar distribution of the meteorological and the surface sea surface temperature and aerosol as the southwest volcanoes. So we also did the same thing for the panel B, which is similar environmental conditions to the east volcanoes. Then let's go to the next.
2 minutes.
Okay, thank you. So, comparison between the southwest volcanoes and the filtered 2014 global data, you can see the N, which represent the sample size. So the global data, which has same environmental conditions, has about 10 times more data than the southwest volcanoes. But if you look at the slope, they're quite similar for both like a cloud fraction and cloud radiative effect. So if we go to next slide, which is a comparison between the east volcano and the filtered 2014 global data, we can also discover the same trend, and so by constraining the environmental conditions, actually the cloud properties react to the ND changes are quite similar. So if you go to the next slide, we actually calculate the susceptibilities between the cloud properties and and ND. So you can see for the red box, the southwest volcanoes, for example, the cloud fraction effect susceptibility is about 0.229, but for the which is quite similar to the global data, which has a similar environmental conditions, which is 0.33. So if you look at the green box, which is a comparison between the east volcanoes and the global data, which also shows a big similarity. So we also checked the science paper we published on 2019, the data. We also calculated the susceptibility to, and compared with the 2014 data between the 14 source and the 40 north and the 40 south. So all the susceptibilities are showing similar magnitude. So let's go to the next conclusion. So this is a summary for the this study. So the cloud properties susceptibilities are substantially larger than previous studies, like previously reported. The GCM has the cloud fraction susceptibility to ND is about 0.01 to 0.15, which revealed by Gan at 2016. And also the Edward also pointed out on in his 2016 paper, which about talking about the meteorological covariability. So actually, this question was answered by filtering the 2014 data by with the similar environmental conditions. So our conclusion is based on 1 and 2 indicates the underestimated susceptibilities in the parameterization of GCMs would result in underestimation of marine low cloud radiative effects. So that's all. Thank you.
Thank you. Okay. Well, thanks very much for that. And thanks also to Jihu for helping us with the presentations today for this morning session. So now we're going to go into discussion. We have about 25 minutes or so for discussion of all the different talks. And I just want to open it up and see if anybody has questions. If you have questions, please raise your hand and want to make a comment, and we can unmute you. So I think it was pretty obvious that one of the key things that came up in a lot of the talks was actually the issue of timescales. And that was very interesting, that maybe some of the differences we saw with across the different natural laboratories or opportunistic experiments have to do with the scales that are being considered and the actual processes and the evolution. We saw that in a couple of talks. We saw that in, obviously that was the main subject of Francisca's talk. Was possibly present in Matt's talk, and Viela Toll also talked about it along with explicitly the work that Ed was doing in different locations, both in industrial plumes and also in ship tracks. And I wonder if there's further comments on that. Is that a framework for actually trying to harmonize some of these things? Go ahead, Bella.
Yeah, thank you. I think Francisca has really done a great job, like highlighting the importance of that. But this is all theoretical in a sense, or LES. Okay, it's not just theoretical, but still. So the question, I think, really is how to observe this time scale, or how to bring LES and observations together here. What kind of observations do we need? Even if you think of some natural experiment, it's not clear what kind of observations for this natural experiment we can use to derive the timescales. So the question really is, what kind of observations can we use to quantify, for example, aerosol enhanced entrainment timescale?
Thanks, Vela. I mean, I'll ask the question then. It seems like that the work that Ed was doing explicitly was showing the change over time, and that could be related. Is that the same as what Francisco was showing with that evolution, where you had some high initial perturbations and then decay over time? Because it would seem that those are the same environment that was being simulated, and that might be something we can use to pick out.
Let me say that we had some works of Francisca today that show the quick decay of the effect in high background. And it can be contrasted with the work of Tom Goren, who tracked the ship tracks over more than 2 days and show how they expand and amplify actually. So I don't think that it is one answer fits all. It depends highly on the background.
May I make a point?
Yeah, go for it, Matt.
Yeah, so I like the Tom Goren's work too, because it exemplifies the fact that when you look at these clouds from space, a lot of times you don't see distinguished ship tracks. You see expansive polluted cloud regions that have been caused by earlier ships. And so all of these track studies are obviously missing this component. It could be huge that is not actually taken into account.
Michael, you want to go ahead?
Yeah, as an attempt to answer Vela's question, and I would love to hear Francisca and Ed's talk here, or thoughts here. I was wondering actually if you could do something like what Ed was doing for ship tracks, but for volcanic plumes. I know Francisca mentioned them as a potentially good laboratory for studying these timescales. But I would think that if you're looking at a volcanic plume, you might be able to use distance from the point source of the volcano as a proxy for time, similar to the way Ed did with ship tracks. I don't know if that's being done by anyone yet, but it seemed to me that that's maybe a good laboratory for this specific question.
Go ahead, Ed.
Yeah, no, I think that's definitely a good thing to look at, Michael. I had a vague feeling I'd seen Matt present something on that, but maybe I'm just imagining it. I don't know. It's
So Francisco, do you want to comment on that?
I guess I'm imagining it then.
No, Matt, actually, I'll let Matt comment after Francisco, but he did look at some volcanic tracks with some information that we might be able to use. Go ahead, Francisco.
Yes, so I just maybe want to first make a more general comment. So, I mean, in terms of looking at ship tracks, of course, we need to keep in mind that we also may have boundary effects. So our ship tracks are specific in other aspects. So they're not only maybe limited in time, but also in space somewhat, right? Which maybe effects that need to be taken into account if we compare them to more spatially extended things, which then also plays into the point Velle made of, certainly our simulations were somewhat idealized, right, or somewhat theoretical, conceptual, which may be different when actually looking at ship tracks. And then commenting on Michael, yeah, I think a nice volcano really studied in a straticumulus region would be really nice. I agree with that, and also with the suggestion you roughly made along those lines.
So I wonder if you could get that information out of the work that Manoush was doing, right? Because she was using the Polaron volcano, and that would potentially have those explicit timescales, although the North Atlantic's a little tricky because the flow regime is very tough. So the Southeast Pacific is probably better. We've actually been looking at trying to do this with Kilauea, which is a very steady flow regime, and you get a very nice sort of plume evolution downstream, both from satellite perspective, which we're starting with, and then eventually getting aircraft out there. That's also a place where it's fairly easy to access a volcano. Of course, it's been intermittent the last couple of years, so that's one of the challenges there. Other comments? Go ahead, Velle.
Yeah, so I think there's a question of using geostationary data in general. So I think yeah, it's not that good quality, but I think the potential it has, it really has not been utilized. Like even this large scale statistics, I think the community has not thought of this temporal evolution enough. So perhaps like simple things like large scale statistics based on geostationary data and compared to these relationships derived from MODIS data, for example, something that could perhaps help as well.
That's a good point. Graham, you want to comment?
Well, yes, just a general comment, and it sort of goes back to trying to look at this morning's talks and synthesize. I think there's another theme. Certainly Francisca's theme of the importance of timescales has come up, but I think there's another one, and that is the difference between the sort of climatological study, which we really need for the indirect effect and climate change, and the ship track type study, or let's call it the event study. And you know, Francisca's work highlights the differences between those via the timescales. But I think the other, you know, what came up for me this morning also was the fact that if we fixate too much on case studies, events, large events, large eruptions, volcanic emissions, etc., we're not getting a good sense of what the climatological effect would be. So, for example, if we take a large emission from a volcano and we do the assessments of the indirect effects from that, or the aerosol cloud interactions from that, that does not reflect climatology or the kinds of effects we might get in a climate model. So I think we also need to keep that in mind when we use the natural lab approach, which I like very much. We also have to remember to expand that to the climatological. And in some cases, there's this nice progression that Francisca highlighted from the ship track to the shipping lane to the climatological. So that's another theme that came up for me.
That's a good point, Graham. I think I'll add to that, as you just mentioned, the progression to the shipping lane and the work that Michael Diamond has done is, I think, quite interesting. And as somebody who worries a lot about the global model, it's easy to produce these estimates with the global model. So the nice part about the events is it allows us some traceability down to the smaller scales. And the third point I'll make is that that's a great segue to what we're going to discuss after the break, because we're going to move on to events that are much different in the sense of opportunistic experiments using, for example, the pandemic over the last 9 months, or using trends over time, which do get at the climatological issues that you're talking about. So we are going to actually, I think, come at it with both ends by the end of the day.
I would like to respond to Graham. The paper that Yan just presented actually compares the perturbations from volcanoes to the natural perturbations due to covariability, and shows that actually this kind of concern is not so much that the volcanic perturbations are not may not be applicable to global aerosol effects is actually not so. We don't need to worry about it too much. We have indication that the perturbations are the same from volcanoes and from other aerosol sources.
I think I'm really talking not about the source material, but more the magnitude of the events. I mean, I find the strong events very interesting because one can learn a lot from them, but they are. We're learning about ship tracks. We're learning about large volcanic emissions, and I think we have to bear in mind that there is the broader aspect of climatological effects from widespread pollution that may, in the end, be a lot more diffuse and not have nearly as strong an immediate impact.
The susceptibilities are actually addressing it to some extent.
Yes, but I think one has to think of the susceptibility as something of a potential, right? You should think of it perhaps as a change in albedo per change in drop concentration. And if one then sort of starts to apply that kernel function, that potential in a patchwork across the globe, not just in the strong emission events, but all over, where the weak responses also occur. And that's what came up yesterday in Jian Hao's work and Xiao Li's work, where they are looking at that covariability in regions like the Eastern North Atlantic or the Northeast Pacific, and getting at that covariability day after day, year after year, sort of incorporating the broader range of effects that could occur, rather than waiting for the grand event, which is by no means not interesting. I am not dismissing it at all. I'm just suggesting we need to be thinking about the hits and the misses, in Francis Bacon's words.
Fine, that's what Yan did. He compared it to those regular areas.
Go ahead, Ed.
Yeah, so Graham, I was just going to ask them what would be convincing. I suppose one thing I was thinking about is you're looking at ship tracks or some kind of event. If you can measure those sensitivities or susceptibilities from those, and they turn out the same as these kind of larger scale susceptibilities or sensitivities that you can measure. I mean, the advantage of the ship tracks and the opportunistic experiments is that you're very clear on your causality. So if you've got a way of linking those to something you've measured in some other way where the causality isn't necessarily clear, but it's perhaps more relevant to a climate scale, is that suitable, or kind of would that be convincing enough that the ship tracks are useful in that sense, or these experiments are useful in that sense?
If these ship tracks are reflecting what's going on, or volcanic emissions for that matter too, if those are reflecting what's going on in a climatological sense, of course, I agree. Francisca's work and your work also now is pointing to the fact that this timescale issue may be important as well. If we this, if we ignore the timescale aspect for a moment, just let's think for a moment it does not exist, and that there's a rapid response, much like TUMI, and there is some indication of these event-based susceptibilities being reflective of climatology, then I think that is meaningful. But I don't think we're there yet, both because of the temporal evolution and because of the covariability piece, which is this meteorology aerosol covariability has not been something we've taken into account sufficiently.
Yeah, no arguments from me there. I'm just thinking about, what would be a nice end state to get to, or where would we like to go?
Tianli.
Hi. Yeah, I like this discussion a lot. So I actually see 3 layers instead of 2. So we have the instantaneous or more close to instantaneous analysis of things like individual volcano tracks or ship tracks or pollution tracks. Then there's a global scale sort of analysis of the statistics. But in between, I think works by, say, Michael or my own work is kind of the aggregated, well-separated at seasonal scale. It's another kind of study. It sort of unifies the two in a sense. It's not the global yet, and I constantly see, like, if you use small scale models to model the response compared to the observations we see at, say, larger scales or smaller scales, there's often a little disconnect. I think that needs to be resolved to sort of use the instantaneous or seasonal scale observations to inform global models.
I think that's a good point. I think what Yanyan Zhu also showed, using the whole, Southeast Pacific during a large volcanic event, but those single volcanic events spread out over the Pacific is not incredibly dissimilar from continental outflow as it disperses over time, right? Because you're talking about similar areas, and the magnitudes are, I guess when they get downstream, they're pretty diffuse, although it wasn't clear that that was quite separated. So I do think it is a challenge a little bit, but you do get the causality.
Can I make a comment?
Yeah, go ahead, Mingwei.
I cannot find the way.
You raised your hand, that's fine.
Yeah. Okay. So I think it seems that our discussion regarding the useless of the volcano eruption and the shipland, it seems we already reached concerns from those results. But my understanding is, different people still have different results, even for volcano eruption and for shiplands and ship tracks. So I think in that sense, we probably still can use. I personally, I would think those type of study can be really important, because we have not reached consensus yet, even for this lateral laboratory. I think that's a better way to isolate or separate meteorology from the aerosol or the covariation. I think Grant just referred to. So I think to really try to understand, to try to separate the lateral variability there. I think we probably want to still keep working on those events, ship tracks, shiplands, volcano eruption. I think in terms of a time scale, we talk about a lot, but I think we also mentioned geostationary satellite, maybe a better tool or tool we can further use to fully understand what's the time scale works here. I think in Francis' paper or talks, I think because that's pretty, I would say, idealized setup, and only a certain case are simulated. So there's still a lot of space and rooms to see how this will be applicable to other situation or case yet. I think, personally, I would think still that's a lot of way I think what I'm trying to say is I think we probably don't want to give up the effort using the shiplands, those type of study to advance our understanding.
Thanks, Mingwei. I think getting back to that, the comment that you made that Viela Toll highlighted and is showing results of is using the new capability that's rolling out with the geostationary satellites that are getting more and more capable, and we're getting more and more
Yes.
comfortable with those
Exactly.
retrievals, which are very MODIS-like in many cases, to actually do a lot of this work explicitly showing the timescales by using geostationary data. That may be the next revolution there, and maybe that's a call to everybody out there to start thinking about that as the next frontier, as Bielo was telling us. But I think the work Matt is doing in this review paper is also highlighting a lot of the commonalities and bringing a lot of these things together and showing these susceptibilities, which I think is coming up with, using these frameworks. I think we're getting to some better sense of this now. Other comments? A few more minutes, and then we'll take a 15-minute break.
Johannes?
Yeah, I mean, it's basically Andrew's question, but maybe I want to point at Yan and ask him because it is a really nice idea to directly link in one study this clear causality of volcanic plumes to the large-scale statistics. But I wonder whether Andrew is not right in that basically your volcanic analysis is just doing the same statistics just over a smaller region, or did you take care that here is a very precise causality in a sense, in plume, out of plume?
Yeah, Actually, we separate the region by based on the mass of concentration of the sulfur compound, but it is just the average of the one degree box during the period. So within this period, it actually has a background also, which is the sulfur compound lower than the threshold. So we actually also compared the properties with the background, but I didn't show here because the time is quite limited.
Yeah, thanks.
Yeah, I would just mention too that another aspect that hasn't really been touched upon is the chemical processing of the sulfur from volcanic emissions and producing CCN, and the temporal evolution of that is a really interesting component that could be examined further as well.
Yeah, we've looked at that a little bit in trying to spec out the concepts for doing a study around Kilauea. I think a lot of the conversion is pretty rapid. And then the complexity a little bit gets to be with the aqueous versus the gas phase conversion, which is also different, and the interactions with the sea surface. So there are some complexities there, but I mean, one way around it is you just have to measure CCN, or some other method of measuring the sulfur that's present at any given time, which to some extent we can do from satellites. It's been harder. TROP-OMI may give us a clearer picture because it's much higher resolution, so it can fit in around these cloud decks. We'll get more data out of it as people start using it rather than the OMPS or the older OMI. TROP-OMI has it's like a 1 kilometer footprint or smaller. So it's almost the same size as MODIS, which will be helpful. But yeah, it is a little bit of an issue in trying to understand the actual perturbation that you're seeing, or what the aerosol actually is. But that's where some of the field measurements come in and are important too.
You're probably becoming oxidant limited in those plumes, right? I mean, you probably don't have enough hydrogen peroxide for the conversion to sulfate.
You are. Pretty much, but once they get aqueous or over time, I mean, it takes a couple hours, right? So you're oxidant limited in those, but it's on the order of, I think we looked at it. It's the conversion is on the order of, several hours to a day. You get a lot of the conversion, and then it starts to asymptote. But yes, you're right. You do get oxidant limited in the early phases in these strong plumes. That's mostly a volcanic issue, I think, for these large effusive eruptions. Not so sure it happens in a ship track, for example. Okay, well, that brings us to about our time. Well, this has been a great session. So thanks to all the speakers. Thanks also to, again, to those helping out and to the presenters. And we're going to take a break for about 15 minutes, and we'll be back at 10 minutes to the hour with the next part of the session that's going to go on to looking at longer term opportunistic experiments from the pandemic and also from longer term trends. So everybody take a little break, balance your fluids, and we'll be back with you in about 15 minutes.
Andrew, do we want to take a screenshot? Okay, we already got
another picture.
Yes. Probably, I think we want to do it every day, basically, because we will have
we can take another quick picture. Yes. So don't go away. Sorry about that. Everybody turn on your camera if you can. And
is someone going to go through and find the best picture of me and everyone else, right? Like, you know.
Yeah, Ed, you can submit your own little. You can submit your own little picture.
Thanks.
And we'll do that.
I've got to get my hair right. You know, it's like.
Right. So everybody, get ready to smile. 1, 2.
Ed, that will be way too much work for you.
Philip can sit there and work on his hair for a little bit. Okay. All right, now we'll take a break and we'll see everybody later.
Thanks.
Does he have much more hair to work with, Andrew?
Andrew, am I moderating this session?
I think so.
Sounds
if you
good.
would.
Yeah, no worries. All right, we are at 14:50. So we're going to begin again, and this theme will be COVID and they are 6-minute talks with 2 minutes questions and answers. And Andrew Gettleman will start us off. Take us away.
Great, thanks, Matt. Thanks, everybody. So this is a little bit of a change. I'm going to report on some recent studies we did on the aerosol climate impacts of COVID-19 induced emission changes. And this is work that I did with Robin Lamble at Imperial and Piers Forster in Leeds, also Duncan, Watson Paris in Oxford, and then Chuck Bardeen and Jack Chen at NCAR. Next slide, please. Going to use these graphics to indicate the pollution and the COVID effects as we go forward. Next slide, please. So as you can see from the little graphic, it's been a roller coaster for all of us over the last year. This is actually changes in mobility from Apple devices. You can actually, Google also does this. And it's very interesting because obviously you see the early part of the pandemic, very sudden changes in the spring of 2020, gradual changes over the summer, reductions again and more lockdowns in much of the planet, and then sort of a gradual recovery as to where we are now. And this has obviously had significant impacts on emissions. Next slide, please. So there's been a number of different observations, both anecdotal and more quantitative, of air pollution. We've all seen lots of pictures like this, where obviously this could be meteorology, but if you just sort of try to compare different times, you see that we did have particularly in the spring of 2020, there was quite a bit of clear skies. This is looking at data from TROP-OMI from a satellite data showing 2020 and 2019, and just the NO2, which was one of the often transport related. So has some of the largest impacts, and you can see big differences in 2020 over most of Eastern China in January and February as severe lockdowns occurred. Next slide, please. So you can use the sort of mobility trends along with emissions to actually then scale the emissions. And so Robin has done this for a bunch of different species. And this shows the percentage emissions reductions. And it's an early estimate from mid 2020. So it shows the early part of 2020 with the first part of the pandemic with the big lockdowns. And what you can see is the reduction in air pollution. Actually get my annotation. So you can actually see, you can see my mouse, the reduction in air pollution that's actually occurring. And you can see that happening in black carbon.
Your mouse, you need to annotate.
I need to annotate, okay. I'll just do the draw. I think that's the best one. Thanks, Danny. You can see these impacts on black carbon, mostly in India, and on VOCs throughout most of the Northern Hemisphere. You can see the nitrogen oxides actually are transport related. So you can see ship tracks in here and actually even a few aviation tracks. Next slide, please. Next slide. Thank you. This is specifically aviation, for example. And so this just shows flights by year. And this is actually 2020. And this is the complete year of 2020. It's from Flight Radar 24. So on the upper right is a aviation water vapor, basically a earlier inventory that we can then scale weekly with this reduction. And that's what we've done to look at that. So you can see aviation dropped about 70% at its peak and has gradually recovered throughout most of 2020 since then. This is not passenger load. This is just total number of flights. Next slide, please. So that's what aviation, what COVID changes sort of did to emissions in different respects. How can we actually estimate these impacts? And so what I'm going to show you is a quick view of some tightly constrained and nudge model simulations. And I'm using ensembles to understand the significance. The conclusions are that reductions in emissions probably warmed the planet a tiny bit through aerosol cloud interactions. That was somewhat offset with reductions in contrails. Interestingly, 2020 was the warmest year ever, and COVID might have contributed to this. And we'll see because the results are actually in two papers, one in GRL and the other one was just accepted to ACP, and there's some references at the end in the last slide. Next slide, please. So I'm using two Earth system models, CESM2 and ECM6, which Duncan ran at Oxford. We're using interactive atmosphere and land, fixed SSTs, and we've actually nudged the meteorology to 2020 to make sure that we sort out any weather effects. These are about 100-kilometer horizontal resolution. CAM is 32 levels, but we're using two-moment microphysics and aerosol models for both of these things. We're using ECM-HAM, that version. And we're doing ensembles of simulations with 20 simulations each. We're looking at COVID reductions versus what would have been a normal emissions year. And we're including aerosol, where there's two sets of simulations. One is aerosol simulations, and with CESM, we also have a contrail model we put in contrail simulations. And then we put this all together with a simple emulator for climate models, the FAIR climate model emulator, to get a better sense of the evolution of temperatures over time. Next slide, please. So just some quick impacts. If you look at the top panel, that's the global average aerosol optical depth change. There's a couple of different simulations from CESM in the green, orange, and blue. And then actually the red line is from ECM. So we're actually getting, with the similar emissions, we get a very similar response. That leads to a net energy change throughout most of 2020, where we get increases of about something like 0.25 watts per meter squared. So that's about 10% of total human effects and a much larger percentage of the total aerosol effects. This is a warming from the drop in AOD and the reduction in ACI globally. So cleaner skies might have actually warmed the planet. These simulations do include direct effects. It's just the indirect effects dominate. Next slide, please. These are the temperature effects, and we're using fixed SST simulations, so you don't see much over land. And the dots indicate significance. So not much of this is significant. We see small significance in some regions of the Northern Hemisphere. They peak in May, and this is about 0.3 Kelvin over land that we're seeing. It's a much smaller global effect over land. Next slide, please. And these are the contrail effects. So these are annually average contrail effects. We have data for all of 2020 just with CESM. You see a reduction in ice water path in the upper left. That leads to a change in the ice number concentration in the upper right. Also a change in high cloud fraction in the lower left, and an overall decrease in land surface temperature, which is slightly smaller than the contrail impact. The contrail impact is slightly smaller than the overall impact of ACI. And this cooling effect somewhat offsets that. It's about half of it or a little bit less. So reduced contrails, less ice number, fewer cirrus clouds, that's a net cool. Next slide, please. And then you put it all together, this is the sort of simple climate model approach where we put in the contrails, and you can see if you put in the magnitude of this, the aerosol effects actually pretty much dominate this over time. First, the initial spike, and then assuming there's some assumptions that we made about how this tails off over time, but you can see that basically the aerosol effects dominate pretty much the other impacts of the pandemic, particularly things like CO2 or tropospheric ozone. We did see reductions of about, I think it was something like 6% in annual emissions of CO2 over the year, but the contrail changes, that would end up being a cooling, but the ACI changes end up being a warming, and that dominates. So next slide, please. So the summary is that we see a small global effect. Interestingly, 2020 was the warmest year ever. This might have just put it over the edge. It's a very, very small effect, but we can use these ensembles and tightly constrain them to actually try to sort out these perturbations and the impacts of small perturbations, which I think is a pretty unique tool. And again, CO2 and contrail reductions would have resulted in cooling. The aerosol reductions would have warmed the planet by changing clouds, and the aerosols dominate on the short term. So notice that these are too small to notice. They're smaller than the weather noise, but this shows a way to think about these small perturbations in climate model simulations, and the ensembles and the perturbation method, I think, is key for this. And next slide. And these are the references. If you just search on Gettleman COVID, you can find these. One's in GRL and the other one is in ACP, and it just got accepted, I think, yesterday. Thank you.
Thanks, Andrew. Great talk. You have several questions in the chat, and in the essence of time, I think maybe we will move on. The next speaker is Johannes Klaas, and feel free to go when you're ready.
Thank you. If I had that amount of results that Andrew showed, then this well, anyway, I mean, we have studied only one single of Andrew's things, which is the one on COVID, and Ed is one of the co-authors here in the room. Next. Yes, and that's data which Andrew also used when he looked at the aircraft impact of the COVID shutdown. So don't comment much on this, except to say what is the color scale, which is a peculiar color scale. So obviously, in order to tease out from data a signal in clouds, we need to average a lot, and that's what I'm introducing here. So we look at the northern hemisphere mid-latitudes between 28 and 65 north, and then divide that entire region into 5 equal areas. And these are chosen such that the change in flight track density between 2019 and 2020 covers, I mean, the 5 quintiles of that change cover this area. Yeah, so white is the 20% of the northern hemisphere mid-latitudes where no change occurred, and yellow a little change, and then light blue a lot of change occurred. So that's where we expect the effects. Next slide, please. And then we looked at MODIS cirrus fraction, and we looked at last year's spring, boreal spring, March to May. And that's the result. And of course, because this is done in the infrared, we have 4 MODIS overpasses, 2 on Terra, 2 on Aqua. And that's the error bar. And that's just the average over the regions and over the season. And basically no result here really, except that we see these regions are, I mean, where the air traffic and its change occur are different regions with somehow different cirrus coverage. Next slide, please. And then we compared it to the climatology, looking at the past 11 years of MODIS data between past 9 years, 2011 to 2019. So not yet the COVID year. And what we see is also in the climatology, we had a pretty similar distribution, but there were differences last year compared to this climatology. Now, why is that? One aspect is obviously what we want to attribute, the change in aviation, but the other aspect is, of course, weather was different. And that we try to account for by looking at the circulation. Next slide, please. And that circulation analogs, they looked in each grid point, MODIS, 1 by 1 degree pixel for each day. So it's a lot of analysis done here. At a stencil of 5 by 5 degree grid boxes around that grid box, the pattern correlation of the 500 hectopascal geopotential from reanalysis. And then we looked into the past 9 years, 2011 to 2019, to seek any days in that in springtime periods during this period when the circulation was similar for each grid point each day. So that is trying to control for the weather. Yeah, not perfect, obviously. I mean, we all know clouds are not simply controlled by the 500 hectopascal geopotential, but to some extent that defines what cirrus would we expect. And that's the orange bit. And what we see, it works to a decent extent. So where we don't expect any change due to aviation, which is on the leftmost quintiles of the distribution, they match. Last year was not very different from the climatology, but where we expect not just a difference due to weather, but also a difference due to the air traffic, which is the rightmost bits of that plot, we see a difference. Next, please. Next slide. Yeah. Also, sorry. One thing to note is, of course, air traffic also has seen quite a strong trend, actually an exponential increase over the period we look at here, 5% per year increase. And so that's what we plot here. So this is given in the years 11, 12, etc. to 19, and that's also in rainbow colors to identify a possible trend. And on the top numbers are even giving the linear trend. What you see is little happened in terms of a trend, which could have been attributable also to climate change or whatever, natural variability, where there was no flight traffic, but in the area where there was a large flight traffic change, it's also a lot of flight traffic happening, we see a significant positive trend. And if we use the numbers, actually the numbers of that train, the change due to the trend, and the numbers due to the decline while COVID, they match. Next slide, please. And that's now taking the difference between the circulation analogs and 2019. We not only looked at cirrus fraction, but also emissivity, sort of the opacity, if you like, I mean, indirect effects. And Matt unmutes himself. I need to hurry up.
2 minutes, sorry.
It's like the speaker standing up is unmuting himself. But you see a strong effect, up to 9% relative change. So 9% of the cirrus due to aviation, what we see here. And then final slide, please. Then feeding it into a radiative transfer model to estimate the net radiative forcing. Interesting things, of course, a balance between long wave and short wave, which happens to cancel almost over Europe here. To come up with a number which is not inconsistent with the literature, actually not very inconsistent with Andrew's estimate, by the way. Thank you.
Thank you, Johannes. Are there any quick questions? Would anyone like to speak? Raise your hand. Danny?
Yeah, in Europe, it seems that you said that the solar cancel the thermal. Is it because in Europe flights don't occur at night as much as in the rest of the world?
Didn't look into reasons, but it sounds convincing. Is that the case, perhaps? Yeah.
Like Frankfurt is closed overnight.
Maybe that's not a reason for my result, because we didn't really have much of a diurnal cycle in there. We only had daily values for the flight track density. Maybe that's not the reason for our result here. But yeah, thanks for pointing to good explanation.
All right, great. We will now move on to the next speaker. Yang Cao, feel free to begin when you're ready.
Okay, hello everyone. I'm Yang. I'm going to reintroduce our recent work, and the topic is strong aerosol effect on cloud amount based on long-term satellite observations over the east coast of United States. This work is under the guidance of Minghuai, Danny, and Yan Nian. Next, please. As we know, the radial forcing associated with aerosol cloud interactions contribute to the largest uncertainty to the total radiative forcing estimate. For the aerosol cloud interactions, the Toomey effect is relatively well understood, but the cloud lifetime effect is not well documented, especially in the GCMs. In the meantime, ND is the bridge connecting the CCN and the cloud macro physical properties. And next, please. Recently, Rosenfeld found strong dependence of cloud amount, cloud cover on ND. For a given CGT, the cloud cover increased significantly with the increase of ND. But in the meantime, the ND over the ECUS region shows a significantly decreasing trend. Combining the strong dependence of cloud cover on ND and the decreasing trend in ND, we expect a decreasing trend in cloud cover, but for the observations, there's no trend in cloud cover. Then we want to know why there's no trend in cloud cover. And next, please. To answer that specific scientific questions, we use long-term satellite observations from 2003 to 2018. We use MODIS Aqua Level 2 and Level 1B data, as well as NSAP FNL reanalyze to find the drivers of the low cloud cover. This figure shows why we choose this area, because this area, because the reduction of emissions, there is a significant decreasing trend in AOD. The right box shows our target area, the East Coast of United States. Next, please. With a regression model, we found 4 cloud controlling parameters. They are ND, CGT, LTS, and IH at 950-100 Pascal. We also checked how cloud responds to these parameters. Overall, larger ND, larger CGT, LTS, and IH will lead to larger cloud cover. This figure shows the relationship. This figure show. Next, please. We further check the relationship between cloud cover and ND. What we found is like what Danny found in the science paper. This figure shows the all cases, and for this figure shows in the stable conditions, neutral and unstable. Overall, the cloud cover will increase with the increase of ND. The right panel shows the relationship between cloud cover and the relative humidity. What we found is that in the clean conditions, which means the ND is small, the cloud cover is not sensitive to the IH. While in the polluted conditions, and in the polluted conditions, the precipitation is suppressed. Then the cloud cover is sensitive to the change of IH, and also larger LTS will lead to larger cloud cover. Next, please. We find the key cloud controlling parameters, and we check how these parameters affect cloud cover. Then we check the long-term trend of these parameters. Among these 4 parameters, only ND and IH shows a clear trend. We can see the ND decreased significantly, about 40%, while the IH increased a lot. Then we use the regression model to quantify this trend of these 2 parameters, how they affect the trend of cloud cover. Firstly, this model can predict the cloud cover well. We can see the blue lines, the solid blue line shows the observed cloud cover from MODIS, and the dashed blue line shows the predict cloud cover. And by removing the trend of IH, we fix IH to its climatology. After doing that, the regression model predicts a significantly decreasing trend in cloud cover, and this can be attributed to the change of ND. When we also fix ND, the model predict increasing trend in cloud cover. So we draw the conclusion. Next, please. So we draw the conclusion: the annual mean cloud cover shows no significant trend due to the cancellation from the opposite trend in ND and IH. And also, only when we fix the meteorologies, we found a significant aerosol effect on cloud amount based on long-term satellite observations. And this paper has been published in JIL this year. Next, please. And also, what we want to do next is to quantify the aerosol effect on cloud amount based on the global scale, and also use more complicated model like deep learning to quantify the effect. This map shows a long-term trend in AOD from 2003 to 2020. That's all. Thank you.
We have a couple questions in the chat. One by Rob. Why does relative humidity decrease in the planetary boundary layer?
Actually, the edge increased. We attribute to we found the warm advections increased and the over that area, and the increased warm advections will lead to stronger inversion layer over the lower boundary layer, and then the stronger inversion will trap more water vapor in the lower part of the boundary layer.
Okay, thanks. There's a couple more questions in the chat by Andrew Williams and Allison Douglas, but feel free to answer those. And thank you very much. And we can now move on to our next talk by Daniel Grosvenor. Take it away.
Okay, hi. So I'd like to talk about the shortwave historical time series. So time series of historical shortwave fluxes in the North Atlantic region, and what's controlling them according to climate models. So next slide, please. So I've been looking at the UK Met Office model. So the UK Earth System model from the CMET6 archive, which is a free-running coupled model. So we can simulate the feedbacks between forcings and the ocean and sea ice, for example. We've got 16 members in this ensemble. I've also been looking at the DA-MIP experiments, which are single forcing experiments. So for example, aerosol only forcing, greenhouse gas only forcing, or natural aerosol only forcing experiments. And they're based on the Hadgen model, which is pretty similar to the UK ESM. And also coupled, but they only have a 4-member ensemble here. Next slide, please. So here are just time series from the UK ESM model. So on the top, we have the shortwave, top of the atmosphere, upwelling flux. And we can see that generally there's an increase between 1850 and 1970, followed by a fairly sharp decrease. And actually all the other variables that I'm looking at here, which are going to be the drivers for this shortwave, these shortwave changes. So we've got clear sky fluxes, cloud drop number concentrations, total cloud fraction, and liquid water path. They're also following similar patterns where you get an increase up to about 1970 and then a decrease. So the question then is, which one of these driver variables is causing the change in shortwave flux? Next slide, please. So to answer that question, I've done some offline related calculations where we try and reconstruct the shortwave top of the atmosphere fluxes using those driver variables as inputs, using a simple related calculation. And the black line is what we get as a result of that. So it captures the variability pretty well and also the trends. So it seems to do a reasonable job there. So next slide, please. And these are the results of what drives those changes. So if you look at the first bar here, this is for period 1, 1870 to 1970. And you can see that the biggest contributor there is the ND, or the cloud drop number changes. So the change in cloud drop number is having the biggest impact on the change in shortwave for that period. There's a small contribution from cloud fraction and liquid water path and clear sky fluxes. But during period 2, there's a much bigger contribution here from the cloud fraction, FC, this cloud fraction. So next slide, please. So here, but then we're also interested in the effect of the, should I raise my annotations? The effect, what's actually driving those changes in the different driver variables. So this is where the DA-MIP experiments come in. So we've got the top is showing the shortwave flux again from the DA-MIP aerosol only forcing here in green, and then the greenhouse gas only run here in black. We can see that they have equal, they have opposing effects on the shortwave fluxes. So the aerosol is driving an increase, and the greenhouse gas is driving a decrease. And during that first period in the DA-MIP aerosol only experiment, it's mostly the increase in CDNC that's having impact. And the second period after 1970, so around here, 1970, in the cloud fraction plot here, you'll notice that the aerosol cloud fraction in the aerosol only run is fairly constant, whereas you get a decrease in cloud fraction in the greenhouse gas run, the black line. And so it's that decrease in cloud fraction that's having the big influence in this second period, according to these runs. So if we go to the next slide, and here I'm summarizing that in terms of a bar plot. So if you look again, just the first bar on the left, it's period 1. So the total of these three, ACI, ARI, and feedback, is the overall aerosol change in shortwave from the DA-MIP aerosol only run. So that's the increase in shortwave due to aerosol. So that's much bigger in that period than the decrease that we get here from the greenhouse gases, GHG. In the second period 2, 1971 to 2014, there's very little aerosol contribution and quite a big, it's all down, and the decrease in shortwave there is due to the greenhouse gas contribution. And then, as you can see here, I've split the DA-MIP aerosol only run contributions from that into ACI, ARI, and feedbacks. So that's done using other simulations, nudge simulations, where we try and fix the meteorology. And so that gives us the ACI and ARI based on runs where we don't have any feedback between the aerosol and the ocean or atmospheric circulation. We assume that the rest of this, so from that we get less than half of the overall change in shortwave. So I guess I'm assuming here that the rest of that is due to changes in the ocean or atmospheric circulation induced by the aerosol. So it's quite interesting that we get quite a much bigger response. Most of that change is coming from those feedbacks. Next slide, please. So I'm just going to conclude with the take-home messages. So we split the time series into two periods, 1850 to 1970 is the first period, where the shortwave flux increase here is mainly driven by Tsumi effect, so that's increases in cloud drop number concentration, driven by the aerosol emission changes, which we saw from the DA-MIP aerosol only run. There is a cloud fraction increase due to the aerosol in that run, but that's diminished by the reducing cloud fraction in the greenhouse gas only run. So the greenhouse gases have the effect of reducing cloud fraction, which opposes the increase we might expect from aerosol effects on cloud fraction. So during the second period, 1971 to 2014, the shortwave flux change is mainly driven by a reduction in cloud fraction, which is driven by greenhouse gas emissions. And that's dominating over any change in aerosol. And actually, the aerosol effect looked to be quite small over that region, over that period. So this actually, I guess the implications for that are that it might make it difficult to use that period, that later period, to infer the effects of clouds of aerosols upon clouds using satellite data, using long-term trends, if most of it's driven by greenhouse gases. Yep. And that's a bit of a shame, because that's the period when we have these nice, we start to have satellite data. But I guess there is hope that maybe we can use more localized. This is looking at the whole Atlantic region, or North Atlantic, maybe looking at more localized regions like in the last talk might give a way to use satellite data to do that. So maybe there is some hope, hopefully. And so yeah, I'll finish the talk there. Thanks for your attention.
Thanks, Dan. Are there any quick questions from the audience?
I guess I'll ask it. Oh, Rob has a question.
Okay.
Yeah, Dan, interesting analysis. It just seems very strange, fortuitous that the trend in ND, you know, the the switchover in the slope is exactly coincides with that in cloud fraction, where the cloud fraction starts to decrease. And yet it's attributed to greenhouse gases. I don't know, do you find that a bit unusual?
Yeah, it makes life a bit more difficult. Yeah, it is strange. I guess there isn't much of a trend in the early period in cloud fraction. In 1970 is when, there's a big change in aerosol. I guess it's just the time when the greenhouse gases were also ramping up, and having a big effect on it. If we look at the DA-MIP time series, that gives us some idea of what's going on. If we go back a couple of slides, we've got time. But yeah.
No, it's interesting. Yeah.
Previous. Yeah,
Cool.
I've already got time.
Yeah, thanks.
Great, thanks. So we can move to the next speaker now. The final speaker. This work will be discussed by Daniel McCoy. Take us away.
Okay. Yeah, thanks. So in this talk, I was going to summarize sort of highlights of these papers we've published over the last couple of years, one led by me, one led by Isabel. And the sort of overall purpose of these papers is to assess some sort of response of cloud droplet number concentration to aerosols, so DND, the aerosol term, and then we scale it by some albedo sensitivity to ND calculation and get a constraint on RFACI. And we take this approach in a couple of different ways. In each case, we're using the cloud droplet number concentration from MODIS. And so first, we just look at the time-space covariation between an aerosol parameter and ND. And then we look at trends where, as we've discussed, it's a little easier to assign causation. And then we look at the spatial pattern where maybe it's a little easier to infer something about the pre-industrial state. Next slide, please, Ping Ping. Thanks. And so first, just the covariation. We did a paper on this where we looked at covariation between cloud droplet number concentration and various aerosol reanalyses in the boundary layer from MIRA-2, which is a really cool data set. I think we discussed it before in this conference, but it uses realistic-ish emissions and runs them through GS5 and nudges to AOD in addition to meteorology. So it's sort of a mix of things that it knows about, but it is essentially a way of speciating and telling you where the aerosol is in the atmosphere. And we use the Grosvenor and Wood 2014 cloud droplet number concentration, as is shown at the bottom right, or bottom left, my apologies. And we looked at a bunch of different regions, they were the white boxes there, but sort of the big takeaway from this was that sulfate and cloud droplet number concentration co-vary strongly, following a power law relationship, as you can see on the right. And so each of the colors is a different white box. And we looked at other aerosol species, but kind of the big takeaway is that sulfate and ND follow this power law relationship. Next slide, please. And so one of the interesting things about this is that there's not a lot of ability to assign any sort of causality with this just multiple linear regression approach that we took to relating aerosol from MIRA and ND from MODIS, but trends can kind of do that. We have a long enough data record now that we can look at decadal trends. And what we do is we look at the MODIS trend, the sulfate MIRA-2 predicted ND from that log-log relationship I just showed you. And we look at SO2 in the boundary layer as sort of an ancillary. And we looked at strongly anthropogenically perturbed regions and regions with a lot of volcanism. And in general, the MIRA-2 sulfate does a pretty good job. The blue line does a pretty good job of predicting the black line, which is the actually observed ND. And it agrees with the OMI SO2 measurement. So that gives us some confidence in these results. So you can relate some of these wiggles to things that have like causal relationship, like emissions control legislation or perhaps eruption history. And so sort of my takeaway from this is that this power law relationship we get from the covariation is actually kind of able to explain these causal things. Next slide, please. And so the natural, inclination here is to calculate some sort of forcing from this. And what we do is we just take that relationship, that should be d log, but you get the idea. And we multiply it by the change in sulfate from the AeroCom model. So we have to use a GCM to infer the pre-industrial state, but it's the best we can do here. And then we do some calculations to get the upwelling shortwave. So we just plug that all together and we get an RFACI that, depending on the sort of uncertainty range, that parallel relationship and sulfate changes, is between -0.5 watt per meter squared and -1.8 watts per meter squared. I should say that includes other aerosols, not just sulfate, but I'm just showing this abbreviated version for simplicity. Next slide, please. So the first part of this first paper I was showing has to assume things about the pre-industrial state kind of really strongly dependent on the GCMs we're using to get that sulfate change and other aerosol changes. So one thing we can do is we can just sort of use the present day pattern of ND to infer something about the pre-industrial. And this is sort of the really 0th order sort of model that we have in our mind for this, is that there's a lot of emissions in the Northern Hemisphere, so ND is perturbed there, and there's not a lot in the Southern Hemisphere, so they look kind of like the pre-industrial. And this is really consistent with like things that Ken Karzal's group at Leeds have shown. And so the inclination here is to say, well, north-south differences are kind of analogous to pre-industrial present-day differences. And of course, this isn't perfect because there's continents in the Northern Hemisphere and so on, but the idea is that it's sort of a first cut at getting you a reasonable constraint. Next slide, please. And so if we look at the AeroCom models and we look at the pre-industrial present-day cloud droplet number concentration, it looks about right. Looks like our kind of simple model we had in our head, where the red line and the blue line are really different in the Northern Hemisphere and pretty much the same in the Southern Hemisphere. And so what we do is we just take the Northern Hemisphere minus Southern Hemisphere difference and ND between those dashed regions I'm showing, and we compare it to the black line, which is the observations. And one thing you might be noticing here is that the black line is really, really flat between hemispheres, which is kind of surprising. Next slide, please. And this is just sort of a thing about the Southern Ocean, is it has a really high cloud droplet number concentration inferred by satellite. It's pretty consistent with in situ measurements, other satellite measurements, and it seems to be mostly biogenic. So in the summer, it's really high, and then it kind of all goes away in the winter when phytoplankton activity dies down. So pretty interesting there. And next slide, please. So when you plug all this into a PPE, so this is a perturbed physics ensemble developed by the University of Leeds. And so each ensemble member calculates an RFACI, and we can calculate a present day hemispheric contrast between north-south ND. And what you can see is that the RFACI follows the hemispheric contrast ND, basically how we'd expect. Where if you have a big hemispheric contrast, you perturb Northern Hemisphere ND a lot, and then you're going to have a big RFACI, a big negative, brightening signal. And thanks. And so the dashed or the gray area is the observational constraint, so it's way over to the left. And this results in a -1.2 to -0.6 constraint on the RFACI. So next slide, please. One of the things that's sort of satisfying about this is that when you put this constraint together with constraints from both papers I talked about today, and you compare them to the 2020 assessment range by Belwan et al., they're all fairly consistent in sort of a center range here. So I found that sort of satisfying. Thanks.
Thanks, Daniel. Are there any questions this talk from the audience?
Oh, I do see that there is. Yes, I saw your question. If you go, I think 1 or 2 slides on, I have a supplementary slide for that. So this is an older slide just showing that the MODIS ND is not, too crazy. I believe it's kind of hard to see on this slide, so I apologize. This isn't a great supplementary slide. The triangles, which you can kind of see in here, are Jasper off cap, and they are made, it's not great, sorry. In the supplementary material, we remake this figure with the Jasper off cap Antarctic Peninsula measurements and the cloud droplet number concentration. From that is pretty consistent with MODIS. So
Thank you.
Ming-Wai, did you have a comment?
Yeah. Yes, thank you. No further comments.
Okay. All right, great. So that concludes our talks for this session, and now we will enter into discussion. We have about 35 minutes. Andrew and I both have meetings that start right at 9, so we'll promptly have to leave at that point. But for the first maybe 20 or I guess 10, 15 minutes, we can chat about the science themes we've heard so far and raise any discussion around that. And then maybe for the last 10 minutes, we can discuss sort of next steps that we want to take with the ACPC low cloud themes. So at this moment, feel free to raise your hand and we can unmute and have a discussion. Johannes.
Yeah, not really a question, but rather something to share here. We in a European project, Constraint, led by Piers Forster, we were discussing, and also in some discussions inside IPCC, discussing these what happened to the aerosol since 2000. So MODIS, if you look at aerosol optical depth and also fine mode, in particular fine mode, by the way, in many regions you see a decline in drop number. I mean, Ribucherian and we had a paper last year. Drop number is consistent in most areas. Emissions go down, etc. And yet, and I think that's a little bit consistent. I don't know. I asked Dan offline, but didn't have the time, obviously, to answer. Seems to be that maybe the energy, the energetic effect was very small. I mean, that's work done by a couple of people who looked at the ocean heat content, and it didn't show a speed up in the increase in ocean heat content. So it's just something to wonder about and maybe discuss, because I think there's pretty strong evidence that there should have been a positive forcing since 2000.
So I think to Johannes' question, I'm not sure whether say like what we found, some nature variability or some other climate change that cause opposite say trends in cloud fraction. I think that can easily compensate the real signal we may see from aerosols. So I think probably it's quite important, even when we use long-term data, like not that long-term, 20 years, 30 years. If we want to fully to figure out the signal from aerosols, I think we have to consider the meteorology. I think like what Johannes did, say when you try to see the effects from trail, that's the same idea there too.
You mean even unforced signals, just natural variability, even over 20 years, is perhaps large enough to explain this?
Yeah. Like the relative community, I think in Jan's talk, that's quite significant. We think how it affects on the cloud fraction trend over the east coast of the US.
Decline in relative humidity, yeah. Mm.
I mean, increase in relative humidity. So that compensated the decline in ND, the decline in cloud fraction that might caused by ND. I mean, at least that's what we sure from our results.
Mm.
Yeah, because I think it's, as you said, yeah. So the decline in ND is quite significant. So then we would expect to see a substantial signal in like radiative flux energy balance, but I think as you point out, we seems we do not see much of that. So I think it would it would be nice to really understand what's going on there.
So I would note two things with that, Johannes. One is what a variation on what Ming-Wai just said. So you have an ND change, but the greenhouse gases are doing a lot. So one is just that the amount of forcing over the last 20 years is also fairly large. So you're just adding a little bit onto an uncertain amount onto an even more uncertain trend. and finding that in the ocean heat content, I can see would be hard, number one. Number two is that significant trend might also be inducing cloud feedbacks over the ocean, which might be manifested as we're discussing through the relative humidity or from other things that we might see. So if we are getting significant shortwave cloud feedbacks that are arising due to climate change, we would also see that potentially as another positive trend in the energetics that would not necessarily be expressed in ND. It's much more likely to be expressed in something like liquid water path or something like that. So I think it's an interesting thought about maybe those trends could be used to help pull these things apart. This one comment that one of the things I've been very interested in and trying to do some work on is trying to understand the intersections between the forcing and the feedback in that regard with respect to aerosols. And so that might be another thing you could use observations for is looking at that trend and seeing if you can pick out things like relative humidity or stability changes that would push clouds in one way and ND, which would push clouds in another way.
Rob Wood?
Yeah, so yeah, thinking along those lines, if the cloud fraction is flat, essentially, is not going down, and the Toomey effect is very strong, it should show up pretty clearly in series as a shortwave increased reflectivity, and so that's a constraint. And so, has that been looked at? I know Dan Grosvenor looked at it, but that was a different region, So I'm curious what the solar reflectivity does over that period for that region where the strong ND decreases.
I think Jan may have some answer. Jan, did you check that? I think we did check at some point, say how the reflectivity might change.
Thinking about the first question, can you say that again?
So did you see the change in the reflectivity, like a two-way flux, the cloud radiative effects? I mean, do you see it significant?
Previously, we calculated the CRE with a radiative transform model, and now we have the series CRE, but I didn't show here, and I think it's quite straightforward to do that, but I didn't get that result. That's
okay,
I will do. Okay, thank you.
Great, yeah, it'd be good to do that. Thanks.
Yes, thank you, Robert.
Daniel Coy, did you want to say something?
Sorry, oops. I was just going to continue on what Andrew was saying about how, depending on what the cloud feedbacks are doing, you might not really be able to see any sort of aerosol effect. I think one of the things I find kind of compelling to think about in terms of that is if you look at the long-term trends in cloud fraction or liquid water path from satellites for the last couple of decades, there is an increasing trend in the Southern Hemisphere, but there isn't a matching trend in the Northern Hemisphere where we've been decreasing emissions. And just sort of looking at those bulk trends, meteorologically, GCMs have a pretty hemispherically identical cloud feedback for abrupt fourth times CO2, but they're not appearing in the observational record, which I think is kind of interesting.
So would that imply there is an aerosol effect that's influencing those trends?
Well, it would imply, I think that would be my inference, is that, yeah.
I find it convincing.
I think I agree. I probably tend to agree too. I think in the Young's paper we just published, we didn't make comments. I think when people try to use observational constraints to derive the cloud feedback, I think they may, I mean, especially when you use the recent observation, they may want to consider the influence from aerosols because that's strong decline in ND. I think that might have influence on the cloud radiative effects. And then if you use the long-term observation to constrain cloud feedback without accounting for the effects from aerosols, that might lead some bias in the constraints.
And it goes quiet. I guess
maybe now's a good time. Yeah, go ahead. Matt.
Oh, I was just going to mention, I guess it's a general question about how reliable are these satellite measurements. We know there's orbital drift, calibration changes over time, and these sorts of issues that keep continually research developing teams are working on. So that's always something to keep in the back of the mind about this.
I wouldn't think Ceres or MODIS is a huge problem. There hasn't been much movement of those sensors that would affect, there's a little drift in time in MODIS, but it's not that sensitive. And I think, Ceres is obviously, they've done a lot of work on making it stable and understanding its calibration. So I would think for these, I think the issue, if it was multiple satellites, might be an issue, certainly before 2002, 2005. But I think the record over the last 20 years, I would think is pretty solid. I don't know if people
and for Clear Sky, they are consistent on top, which is also interesting. Ceres and MODIS are consistent in their trends.
I guess stitching it back to AVHRR back into the 80s can be challenging.
Yeah, most people don't even try to do that. There's not a lot of long-term cloud fraction trends that go before 2000 from satellites for exactly that reason. There's been a couple of
attempts. Unless you ask Joel Norris, of course.
Yeah, except for Joel, right? Joel will do it. Joel's done it, but.
I think one thing that's pretty convincing in support of the cloud fraction trend stitching that Joel Norris's group does is that if you look at the microwave radiometer data, which doesn't really care that much about trend or about drift, sorry, you still get something that's quite consistent in terms of the low cloud trends. And so I think that's in their 2016 Nature papers. They also show that data set.
And just maybe going to Rob's question, I was just looking at a plot I made of the shortwave fluxes from a series-derived data set, so deep sea, going back to 1985. And yeah, we do see there's a negative trend on the west side of the Atlantic, off the coast of the US, but then on the east side is actually a positive trend, which is kind of interesting. But meteorology and dynamical modes plays a big role in that pattern of trend as well.
Yeah, I think the North Atlantic in particular, because we know there's there's even decadal trends there. Well, now might be a good time to transition to sort of general comments and next steps. You think, Matt?
Yeah, I think so. So I guess the main question being sort of where do we want to see the ACPC low cloud themes go, maybe over the next years or so. And, we've had some great sessions on natural laboratories and whether we, keep picking up on that theme and exploring more of the complexities of that, or sort of take a new direction, perhaps. Yesterday, there were some really great discussions around sort of thinking about, how Aerocom can be sort of a model for doing large collaborative intercomparison modeling studies to look at processes. So that could be another thought thread to go along. But I think this is a good time to maybe discuss sort of these ideas.
Allison, did you have a comment?
Yeah, I think that something that I've noticed is that everyone this year has been using different methodology to kind of deal with meteorology and confounding factors, like choosing a point further away from the plume, or accounting for meteorology in the binning, or using not just the linear regression. So I think that would be an interesting review, is just to see how these different methods have worked so far.
Michael?
Sorry, I had a muting issue. Yeah, I think going off of what Allison said, maybe if there was one particular region or analysis, if we just did the exact same thing with all of these different methods and just see how they differ, that could be an extremely useful result. Because we do know have some certain cases where people have looked at the same area and come to slightly different conclusions. So if there was a good single place to start there, that might be helpful.
I mean, it might just be reviewing. Sorry, go ahead.
Well, just following along that thread, I think if there was a sort of repository of common data sets that could be easily accessible to facilitate that, that could be a useful starting point.
I mean, some of this is going to be in the opportunistic experiment work, right? Where we're trying to compare this a little bit, but thinking about what can be done in sort of a similar area might be useful. I mean, we could review that. We saw a lot of things on these different, these different opportunistic experiments, whether it's a lot of it was volcanoes or ship tracks, that people have done different analyses on in different ways on this.
Danny?
I think that focusing on the shipping lane would be a good idea, because that actually encompass the right scale, and we can have a sub-scale tracking of individual ship tracks, and we can research there the impacts of aerosols and meteorology. So I'm not advocating that this particular case will be the focus, but something with the same principles, that we have the right scale embedded in it, and it is well defined and accessible to everyone, and has already some heritage of publications.
Right. Well, we also have the interesting conundrum, which was going to be a subject of discussion last year, but got derailed because other things happened to emissions in 2020, which was the new shipping regulations that went into effect last year. So if we look forward, I mean, it's hard to tell with the pandemic, but looking forward at the shipping lanes, there should be a lot less sulfur down there, or in different places, whether it's off the, I mean, it was obviously, as Ed showed, there was big impacts off the coast of North America and Europe, but not so much in the Southeast Atlantic. And so now the Southeast Atlantic might have some of that changes in sulfur as well. It might be hard to separate until we get a couple years of data, but.
Ed?
Oh yeah, sorry, I think I was, yeah. Yes, no, I'd agree. I mean, I think that's definitely, I mean, there must be an effect from that. And so, especially in the Southeast Atlantic, where there wasn't, I mean, there hadn't been a big change in 2015 because there weren't regulations there. Definitely an interesting thing to look at.
Johannes Klaas?
Yeah, Matthew said AeroCom, but we only need to look at Sue and Philip and the colleagues in this nice model into comparison, which was really informative, in my opinion, looking at the Houston case. So in that sense, I think some joint modeling effort could be quite neat. And maybe Franziska, if we say we are interested in ship tracks, maybe Franziska can give some advice if she was to pick one case, whether there is a certain definition that would be of interest to simulate with a couple of models. I mean, some people use WRF, some use ICON, so we could probably throw a couple of models at a certain case, if there is one.
So I see a couple hands raised. I'm going to go to Philip and then Graham.
Yeah, I think what I would find really interesting, AeroCom is one model, but I think to link this up with the large-scale models would be most interesting. And if, as we are just planning in sort of AeroCom indirect experiment, to really a consistent analysis across scales, some high-resolution modeling that really ties within the AeroCom analysis. And then where we can really say, okay, the observations tell us X, the high-resolution models agree or don't agree on liquid water path adjustments, and the climate models are all wrong or all right. I think we would gain a lot from it. And I mean, we recently dug out the AeroCom forcings again, and just plots, yeah, you can just look at the maps and look at the uncertainty or the diversity in AeroCom, and I think it would guide us relatively quickly to one of the low cloud decks to start from. I mean, you have sort of 3 or 4 to pick from, but that's pretty much what you might want to focus.
Great. Graham?
Somewhat different topic, thinking about the potential for geostationary satellite studies. This has come up, and I don't know whether this group, ACPC, is ready for some sort of a joint effort on, exploring the capabilities of GO16, starting to look at the geostationary view of evolving systems. Maybe it's still something that needs to be done at the individual level, but I thought I'd throw it out as something that those who are more engaged in the retrieval side and have a lot of experience with either polar orbiting or geostationary. I know you, Matt, have done quite a bit with geostationary. So just wondering if that's mature enough for some sort of an ACPC project. I didn't mean to derail the discussion from an AeroCom type modeling effort, but I'd throw that out as well.
Danny.
To respond to Graham, to make it useful, you need to track also overnight, and this is an inherent limitation that we need to overcome somehow. Overnight, we can have some qualitative idea about the effective radius by the thermal channels, but it is not as accurate, but it's still useful, as demonstrated by the seminal paper of Tom Gorin several years ago, when he tracked ship tracks over several days in the North Atlantic. I think that we have discussed it and we emphasized it in CPC previously, and we wanted to associate or to go along with this observation with simulations of the same. There was some of this effort and some of that is continuing, but I think it's time to, we are far from getting what we want from that, and I think we need to continue emphasizing this direction.
Andrew.
Yeah, I think picking up what Philip said, I think it looks like there's going to be, with AeroCom, some discussion of looking at ACI, and I think coordinating that with this group so that we can get the diagnostics at least into the large scale models that we want would be useful, and thinking about how that might be extended across scales in some way for particular test cases. A lot of the AeroCom stuff is discussing nudge simulations, for example. So if we're doing nudge simulations through AeroCom, then potentially there's the opportunity to use small scale models for case studies or regional studies. And I think that would be something we could certainly coordinate to try to get at this thing that, and I think what we came out with yesterday was there was a lot of interest in looking across scales and trying to understand this limitation of the dynamical interactions with the small scale models and the process interactions with the large scale models. And maybe a constrained AeroCom study plus some smaller scale model studies with observational comparisons might be a good place to really try to bridge those scales.
Yeah, I mean, I think that's what it's going to take really to get this timescale problem to understand it, is to bridge the gap between all these scales of variability in models to some extent.
Right, and maybe that's an opportunity to bring in for a targeted focus a year of geostationary data in the recent times that we could use to try to then come at this, with all of our tools and encourage people to get, part of it is, as you said, Matt, get the data sets together so that people can do these studies on a common set of models and suggested data and encourage that and get a variety of different people. Maybe that's the coming at it from different methods that we were also talking about before.
Yeah,
Mingwei had a comment.
Oh, yeah, Mingwei.
Yeah, I think what I think Andrew already said that. I also agree with Philip and Andrew. I think for this group, we do have a very diverse background, and we have global models and process models and a lot of observational people. So I think it's very nice to try to utilize all the wisdoms here to come out with something that's beyond just the AeroCom global model in the comparison. So I think it's a great idea to try to do something across scales, across different model platforms. I think you already just finished the review paper. I think we want to think something for next step. something big for next step. So I would think that type of the model in the comparison, try to link different type models across different scales. I think maybe a good thing for us too. But I think probably a challenge here will be how we want to coordinate that and how we want to coordinate this effort with the ARCOM. Or should someone here to, get in touch with the people from ARCOM, or should I say like one of us try from this group try to lead the ARCOM in the comparison? That probably will make it easier to get the input from this group, and especially to link to the small scale models. I think that would be. But then we probably also, because for ARCOM, for global models, we have pretty mature, I would say, protocol for how to do that. But I think for small scale models, we need to figure out how exactly we want to link these two types of the modeling activity. I think that's just my. I said I like the idea. I think that's great for us to move forward. And then also on the geostationary satellite, I think that we also have room for that, because we have a lot of people who are really working on the satellite observations, small scale processes. I think we definitely have rooms for separate activities that focus on geostationary satellite analysis. I see a lot of potential for using that to answer a lot of the questions we discussed, outstanding questions we discussed today. I also agree with Andrew. I think then there's opportunity for connect this back to the modeling group as well. Thank you.
I hate to leave this conversation because it's really great, but I have to go, unfortunately.
Okay, so 2 more comments, Duncan, quickly, and then Graham, and then we'll close it.
Just quickly. I won't comment on the geostationary, although I think it will be valuable. But in terms of the ARCOM indirect experiment, so as Philip pointed out, pretty much everyone involved here, myself and Andrew, and everyone, Ed and everyone here. So we're happy to coordinate that, and I think I'm happy to, if people just email me and let me know if you're happy to contribute a high resolution model, we can. I'll invite you to the next discussion. It's very timely. We recently picked up this discussion literally last week, so I think having the expertise of high resolution simulations at this stage to help us frame the experiment and exactly what that protocol looks like, I think would be very valuable. So yeah, I think if people get in touch with me, that's probably the best way to start.
Thank you.
Thanks, Duncan. Graham, last word.
Well, just I think Duncan started to get at this. I think if we want to sort of start bridging the scales, we need to have a protocol. Is it going to be individual models doing their own thing, and then us looking at the net, the sum of all those models and how they compare to the larger scale models? Or do we have a protocol that actually sort of tries to have a consistency across these scales with models that have self-consistency? So I think this is really a much longer conversation, which we may need to have offline with a group of people who are interested.
Right. Okay.
I think if I may just very briefly, I mean, one of the valuable things, if we can coordinate them, is that we can potentially use them as a constraint for the Corso resolution models. So we're looking to explore the warm rain processes in these models across parameterization, across their parameter ranges. So that could also be a useful approach.
Okay, great. Well, thank everybody for your time today. Thanks also to our helpers. So Allison Douglas and Isabel McCoy were rapporteurs in the background. Thanks to Jihu and to Ping Ping for sharing the slides. Thanks to you all for coming. And we'll be back again tomorrow. Thank you very much.
Bye.